Hello, and welcome to this section of new features in Wolfram language version 12.2. My name is Shadi Ashnai, and I'm going to be showing new features in image, audio, and video processing and analysis. A quick outline of what's new. We have added a whole set of new capabilities for video generation, processing, analysis, and editing. Animated image is a new object that I'm going to introduce and show. Face functionality have been improved on the image side, image scopes have been added, and a lot more that's going to be discussed. Let's begin with a quick recap of video object. Video object has been introduced as a first-class citizen in version 12.1. Now version 12.2 extends the capabilities beyond what was introduced initially, and this is giving us a rich set of capabilities for processing, analysis, and understanding video objects and video files, as well as obviously collections of video files. What's unique about video object in the Wolfram language? It's completely out of core. We support an extensive list of containers and codec, both for reading video files into our system in order to process them, as well as exporting to them so that we can use them elsewhere. The fact that we have more than a decade of development on image and audio processing makes the video functionality, even in these initial releases, very rich and powerful. Our capabilities are also bundled with powerful machine learning and neural nets capabilities in the system. And as it is the case in almost any field or any feature set that we have in the system, statistics, visualization, and many more capabilities in the system makes our tool, our environment, a unique system and environment for completing any workflow for any solution or application that is desired. The video object remains experimental in version 12.2 until we have more of the design and more of the implementation of functions that we want to have in the system, as well as an in-notebook player, which didn't get released in 12.2 either. Let's take a quick look. Video is a wrapper, is an object that can be constructed either from a file or a URL. We do support audio and subtitle tracks, an arbitrary number of those, as many of the codecs that are out there allow for them. Here is a quick example that I'm creating a video object from an MP4 that is in the layout distributed with the Wolfram language. By default, a thumbnail view is displayed, which upon a click, a default video player opens up and can be used to play the video object. There are two experimental appearances or user interfaces that can give us an access to an in-notebook player for a video object. This is a minimal GUI, which basically doesn't have much controls beyond just the play and pause, and I can go to a basic appearance, which gives me one slider, play, pause, as well as some audio capabilities. We're gonna stick with our thumbnail appearance throughout this presentation. We can look into properties and information of our video object using the function information. In this case, I can get properties such as duration, raster size, which is the defaults to the original raster size of the video, the bitrate used when creating the file, frame rate, and more. We can also extract specific properties of a video, such as duration. We can look into the file and get a list of frames. In this case, I'm asking for 5 frames equally spaced in the duration of the video. We can extract the audio object from video and basically do any audio processing on the extracted audio and so forth. In order to quickly show our support for Codex, it's worth noting that our system relies on FFmpeg. It is already we are already distributing a limited version of FFmpeg with the Wolfram language. However, in order to extend the number of codecs supported in the system, we highly recommend installing FFmpeg version 4 or higher. There is a system options, video processing, try using system FFmpeg, which is true by default. If you have FFmpeg installed correctly on your system, we automatically utilize it. And once FFmpeg is installed and we are using it, which is the case by default, you can see that the number of codecs supported for either of the containers that we support is pretty high. Recently, we have released 3 community posts on Windows, Mac, and Linux, walking through steps needed and checks to do in order to make sure FFmpeg is correctly installed on your machine. All right. In addition to import and export capabilities and the video object itself, in version 12.1, we had small number of functions for doing processing and analysis and editing on a video object. A big feature of version 12.2 is video generator, which is a new function that allows for constructing or creating a video object as long as the user wants from a function that is specified. And we all know with the plotting functionality in the Wolfram language, this is a great tool for creating images from or creating visualizations of any concept, basically. Let's start from a simple example. Video generator can be used to create a constant video if you pass it just a constant image. So in this case, I have, I'm getting one still image of this dog on a beach from our data repository, and I generate 2 seconds of a still image, which is just that from that single image. In addition to that, I can basically start manipulating that one image, and then here I have a list of 3 images that I'm sending to my function video generator. And in fact, let's just switch to the minimal appearance here and look at it in Notebook. And so as you see, the 2 seconds of the video, I basically step through the 3 images that were created. And the function, instead, in addition to a single image or a list, I can basically provide a function that any arbitrary function in this argument of video generator, and for the duration provided, we pass the time to the function as the input, run the function, generate frames, and write them to the file as the frames are generated. So again, this is a very simple example that is basically rotating the image of this dog in the 2 seconds of the video generation. Let's look at some additional examples. For instance, here I have a dynamically updating plot similar to manipulate, but in this case, it's just creating a video, can be infinitely long and so forth. Or here I have a 3D geometry, a 3D object that I would like to look around, and instead of just interactively look around it, I can specify a rotation around the z-axis in this particular case. And just because this takes a little longer to generate the frames, I've pre-computed that, and I can just go around and look at this 3D shape from all over. And then here is another example, which is my favorite. I'm evolving, I'm doing a cellular automaton evolution, Rule 30, which is our favorite. It comes in a lot of examples. I create a set of images that shows that evolution. And then from those set of images, I basically show the evolution of the cellular automaton Rule 30. And then for those who have played with audio in our system, you know that we have already an example data of Rule 30 in the system. In addition to just specifying the frames and creating a single video track file, I can also add this audio object into video generator and basically create a video of the cellular automaton evolution as well as the audio behind it. And in addition to just specifying all of those audio and image specs in the video generator itself, we can also use Video Combine, which was already introduced in version 12.1, which is done a lot in practice. The video is generated separately, like in this case. I go through the images generated in the table above, the evolution of the cellular automaton, for the duration of audio, and then separately add the audio object to that generated video. So let's quickly get my table going. That should be really quick. And if I do the video combine, this is basically giving us the same generated video. Since we have released Video Generator in 12.2, Arnaud Buzzing from Wolfram, which a lot of you may be familiar with him, has created a YouTube channel full of very neat examples. Give me 1 second quickly. That basically shows a lot of the neat ideas for generating audios in our system. For instance, this is one of the first ones that he created. Quickly see if I can get that going, which was taking the data that we're dealing with every day these days, COVID-19 data. And then if I go through, here I'm going through, Arnaud is going through different months. Just a little more quiet. He has added a nice audio in the background and basically shows how the number of cases over the past year has gone up in that video. And as you see, this is almost 2.5 minutes of video showing this change. Another example that is 23 minutes is going through polyhedrons that a lot of them we have in the system. Any of them you can compute and rotating around with a very nice Beethoven music in the background. I'll let you guys to enjoy these creations of Arnaud separately later. One thing that we thought about as we were working on Video Generator, and we have been dealing with all along in the past as well, is all of these objects and functions that we have that generate some file and are backed with a file or an asset. We have to decide where all of these are stored. A lot of times, there are some default locations. For instance, export always writes in the working directory, directory bracket bracket. Some other functions write in other arbitrary places. But it's often very useful to have control over where all of these things are going. Of course, we can export to any location if desired, but it might be nice if we can just from the get-go specify where we would like to write or store the assets that are backing these objects that are being created. Let's quickly look at examples, very simple examples using Video Generator with that same dog on the beach image that I had. In this simple example, when I say, okay, so along the lines of where the asset goes, we have introduced this new option, generated asset location, along with a variable that I can get to a bit later, to basically bring control to the users over where the assets are stored. In this example, as I said by default, for all of our video functions, we currently write functions under this directory, which is my documents directory, Wolfram video. And then similarly, my working directory, Wolfram/audio for audio functions such as speech synthesize. However, with this option, I can as well specify an explicit location. In this case, it's complaining that the file already exists, I can delete it and then write it back. And there it is, where I care for, or I can write it into any other directory without specifying what exact file name, and then a file name with a with a unique ID is going to be created in that folder. A very neat thing about this syntax is that a lot of times I'm working on a project, and my project, I would like it to be contained in some folder, and all of the assets for that as well would be nice if it's in that same folder. So I can say my generated asset location, I would like it to be that folder, or I can say I would like my dollar generated asset location to be that folder. And in that case, all of the assets that are, all of the functions that take this option are going to create their asset into that directory. This is one other syntax, which is basically specifying to store the asset, in this case, the video file, as a local object under the local base. So again, this is something we have been thinking about and working along the ways to get things more under control. I believe this is an improvement to the situation we have had before, and hopefully this is going to be even more improved and more systematically used all along in our system. Okay, now let's look at what capabilities we have introduced for processing videos. Videos often come with quality issues, such as noise or instability. For all of those, people have developed algorithms to improve the quality of a video. And a lot of times people just want to change the content of the video to add effects or annotations, or combine videos with each other to convey a message or show the concept more easily. Version 12.1 had added video frame map, and now version 12.2 is adding audio track apply and video map. Let's take a look at all three of these functions. Video frame map is has basically two modes, and all of these functions, or a lot of the functions, a few of these functions that we have in the video map family have the same flavors. In the two argument form of the function, or all of these functions again, frames of the video or partitions corresponding to frames of a video are passed to the function f. And then we can look at partitions of longer durations, so n frames at a time, that are overlapping by one frame and sliding throughout the video. And then there is often a fourth argument that can specify how much to move ahead at a given partition. So the simple two argument form of this example, let's take an access, get an access to a short snippet, a 10-second snippet of our camera in this example. And then if we run a simple function call to do, say, a color negation of all the frames of this video that we have in example data, we can basically do a frame by frame negation of the video. So we can also use a different flavor of this function, which gets partition of 1 second. Let's quickly change the appearance to minimal for all of the video objects in our system, so that we can display all of these in Notebook. So here is another flavor of the function, which is basically blending frames corresponding to 1 second, which I believe this was at 24 frames per second. So gets every 20 frame at a time and blends all of those frames together. So if we wait just a little, I had it pre-computed, but just evaluated again. All of these functions have these progress indicator, because a lot of these video operations are not by nature very fast operations anyways. So the progress indicator is a very good indicator to know where you're at with the computation. So here, as you see already in that frame, first frame, some blurring has happened over time, or blending. And now, as you see, again, every 20-something, 24 frames, I believe, for this video of the video have been blended with each other over time. So this is a kind of an effect that happens here. So this function basically gives us access to video frames, and we can process them one at a time or a chunk at a time. We have added audio track apply, which basically gets the audio track of the video file and processes that as a one-shot process, and then stick that with the video track as the illustration shows. So this is a whole audio operation, like audio reverse or audio normalize or any other operation that is desirable. So if you recall, we can get access to that audio track by calling audio of the video object, and then, for instance, plot it. And then if I run something like audio reverse, I get another audio to look at the audio. I'm sorry, we get another video object. If I look at the audio track of that video object, it's basically the same signal reversed. And again, any processing such as noise reduction, low pass filtering, or anything else, reverbs and anything else can happen on the video tracks. Now, video map is introduced to be the super function on top of all of those that can get access to any image or video track, audio track, eventually subtitle track, can get a handle to time and time intervals, the time boundaries for each partition and so forth, and allow for even much richer syntax and capabilities for altering the content of a video file. To compare with video frame map, here, this was the simple call for video frame map color negate of video, and these sort of negated video comes back. This syntax is basically equivalent to saying I would like to apply color negate to slot, which is the input of the function, which is the frame that comes in video frame map. The equivalent of that in video map is going to be something of this sort. The reason to that is that since we allow for processing any track of the video at a given time, an association of image, audio, time, and time boundaries are sent back to the function that is specified. So we would have to explicitly say that I would like to process image as the value that comes into the function, that value of the association. And this basically is going to give us exactly the same negated video. And then we can do multiple other things. For instance, as I said, time is another argument that is passed to the function at any given time. So I can blur the frames using an increasing radius for blurring. So if this computation is finished at the beginning, we just blur the frames a little, and as the time progresses, we see more and more of the blurring. It's worth noting that, as you probably noticed, there is no audio included in this video. Video map only produces what is specified with this function. And as I have down below, you can specify what to put in the audio track, and by default, nothing gets injected there. Here is another example that I have that the frames are being processed with respect to some measurement from the audio track. For instance, in this case, we're getting maximum amplitude of the audio track with some multiplier, and then basically make every frame lighter based on that value. So whenever we have basically louder audio, we get brighter video frames as well. These are, again, just very simple examples showing that with all the capabilities that we have from image and audio, this opens up room for basically any computations, any processing, custom processing that the user wants to implement in our system. Again, the same note that I mentioned earlier, initial video has one video, one audio track, the processed version only comes back with a single video track, no audio. And this would be a syntax, an association syntax, which says what to be injected into the video track and what to be injected into audio track, which I'm basically just copying over the audio track. And if I run that, I get negated video with the same audio built in, and this is just the information of that. Okay, that's as much as video processing that we have in 12.2. The work is not done there. More is coming, and I can highlight what are the thoughts that we have for all of video processing and analysis after just in a little bit. Version 12.1 again started the idea that there could be functions and perhaps super functions that allow for video analysis. Typically, video analysis is done on local partitions of the video. The content, the temporal changes, and the temporal understanding, the local understanding of the video content is a much more typical operation in video analysis. And for that, the set of functions that we have introduced for video analysis are very similar to what we have talked about for processing, but just not returning a new video object, returning the result of the analysis. So video map time series, previously in 12.1 named video time series, is a function that basically takes a function that is working either again on single, on partitions corresponding to single frames and their audio, if that exists, and produces time value pairs wrapped into a time series expression, or working on partitions longer than one frame, and again producing time, some values coming out of that function f for each timestamp ti. This example is one of the simplest to relate to. We have the same Caminanda's video. We're doing some computations like getting the mean, not intensity, mean RGB values per frame. Nothing else is being processed on the audio track. And again, this is all pre-computed, but if we do that, we have so many data points from the minute and a half of the audio corresponding to every frame of this video object. And then with a function like datelist plot, we can easily just plot that time series. And since we know the mean values correspond to red, green, and blue mean values for each frame, we can just use such a plot style to show how the values of each channel change over time for this video object. Now, the second typical flavor of these processing and analysis functions, which is taking basically a partition of a specified number of frames or duration, can also be used to compute the distance between consecutive frames. This example, for instance, is showing us what is the distance between two consecutive frames of the video. And whenever this is getting larger, it means that we have some kind of a scene change, for instance. Same concept or the same function with another machine learning backed function such as image cases can be used for counting, for instance, cars, faces, other objects, and so forth in videos. And then after this computation is done, this is a more computationally intensive operation. I've pre-computed the result. We can, again, run it through something like list line plot and see how many cars are detected over time in this video. Okay, so that's for time series. Now, time series has one very important limitation, and this limitation is basically the fact that all of these values V1 and V2 produced out of the function f should be similar in dimension and the head. So either they are basically all of the same type of expression that is being stored, or if they are less, they have to be exactly of the same length. In order to allow for operations that do not conform to that limitation, and we may want to have results that may be varying length over time, we have added a more relaxed and generic function called video map list. Video map list is basically the same, exactly the same syntax as video map time series. The only difference is that the result does not come back as a time series. The result is a list of values corresponding to each of those frames or each of those partitions. Now, here is one of my favorite examples again, where we show that, for instance, dominant colors, which could have varying number of colors per each frame, can be computed using this construct, video map list, per frame. And now, once we have a list of varying length dominant colors, we can flatten them, tally them up, and even show something like a word cloud of those. So all good. However, a lot of times we would like to detect exact intervals of interest. So in addition to these generic functions that give us time series or just the results, video intervals is a very handy function that can specify some criteria and then return the intervals for which the provided criterion is matched, is returning true. For instance, in order to find all the intervals of our same Caminanda's video, I can define a criteria that says I would like the max of that frame, the difference between max and min of the frame to be smaller than a fixed value, for instance, in this case, a small threshold of 0.01. And this gives me some kind of a set of intervals, in this case, 5 intervals at the beginning, somewhat in the middle or towards the end, and at the very end, that I have constant frames, mostly when I have like, either we have transitions or whatever else. And here is another example where, again, I'm getting a hold of data outside of just the video track here, looking at audio track, and then saying whenever I have mean apps value of my audio snippet being larger than some defined threshold, I would like to assume that to be allowed audio. And this computation of video intervals is basically returning intervals that are considered to be loud with this particular specification. And again, I would like to remind that the large number of audio and image capabilities that have been introduced over versions of the Wolfram language is going to enrich what can be done with these video operations. Okay, all right. So maybe before we get there, I wanted to talk about what is coming next. A lot of these operations that we talked about were single video in, single computation or audio, or sorry, video out in the case of video map, for instance. So 2 main things that are coming in most probably next version, if not very soon after that, is going to be multi-video feeds in. So a lot of times we would like to combine multiple video feeds or analyze one video with respect to another. So I think one of the major upcoming features to the set of video capabilities, analysis, and processing is going to be multi-video input. And then parallelization is another thing that we are putting some effort in, just to make sure the functions that we have even more optimized and time efficient. Most specifically because a lot of these arbitrary functions can be easily parallelized on the set of partitions that we can make out of the video file. And the operations most of the time are very much parallelizable, and we would like to leverage that as well. Okay, at this point, I think the hard stuff are done. Let's look at some editing capabilities that are going to be a lot of times very handy to have around to prepare or post-process a video. So video trim was already introduced in 12.1 to get basically just the beginning or end or some part of a video object. And multi-interval syntax has been introduced in version 12.2. So same video, I'm trimming 2 intervals of 10 seconds each. You saw 2 progress indicators there, another improvement. We're going to combine that all into one progress indicator. A lot of work is being done on that to make sure the communication on how much time is left to be done with this evaluation is communicated with the user. Now, with this syntax, 2 video objects out. Video combine, also another function that has been there before, is very useful to combine multiple video tracks, multiple audio tracks, and any combination is going to be allowed, and we end up with a file that has multiple of either of the tracks that has been specified. For instance, here, the example I showed earlier, we have evolution of the cellular automaton shown and generated with video generator. We combine it with the audio track, which is a very typical workflow for video generation. Video join is a function that sequentially adds or joins multiple video objects. The syntax is very similar to all the other join functions that we have. You can have just a sequence specified. They're sequentially added to each other. Here I have a cellular automaton example, color negated version, and then just arbitrarily join these 3 generated videos with each other. Actually, it's not the same example. I just used the last step of the evolution and generated 3-second from alternating color negate or the original. Video split, no examples here. The illustration says it all. I have a set of times, a list of times that I would like to split the video into multiple segments that can be used to do that. Video delete gets rid of unwanted parts of video objects, so whatever is specified there can get removed. This one returns 1 video object with those intervals removed. And that brings us to video transcode, which is a function that can be used to either specify or transcode into a requested, to put all of the video content into a requested container, such as MP4. We have some services such as Instagram and YouTube and so forth curated. More of that curation is going to be coming, which we transcode into recommended specifications suggested by that service. And a lot of times, we simply would like to conform to some known specifications, such as I want my video encoding to be H.264, such a frame rate, such a raster size, and so forth. Video transcode is going to be the go-to function in order to do all of that post-processing and last step wrap-up of our work, just to make our final production ready to be used in any platform. So here is one example that we have. This Wolfram example is a specific video that we have created for the purpose of our documentation and demos. This one has a single bullfinch video of a bullfinch on a tree, 3 audio tracks, 1 with the original sound of the bird and 2 with narrations of the spoken form of the 2 subtitles that we have that talk about the Eurasian bullfinch. And for instance, this video was created with a VP9, Vorbis audio encoding, and the specified sample rates and frame rates. I can run this video through video transcode to get the most typical H.264 AAC. In this case, the container ends up being MKV. If I want to do an MP4, which is again the more typical container, I can do that as well. Same data, same encoded data comes back in the requested codex. The container is ends up being an MP4. All right. For those who have heard us talk about our video introduced in 12.3, we had some track selection capabilities through 3 options: audio tracks, subtitle tracks, and video tracks. To emphasize on the fact that we are ready for whatever people generate out there in the wild. Although videos with multiple video tracks are not very common out in the wild, we are prepared to handle them and process them and get access to those tracks. Unlike video tracks, it is common to want to have multiple audio tracks, very much used for translations into different languages, as well as subtitle tracks, which is a lot of times, again, either the closed captioning or some additional information that gets displayed on demand on the display or on the screen when the video is being played back. In our system, by default, all tracks are assumed to be there, present, accessible, and ready to be processed, analyzed, or anything else. For instance, in this particular case, our video object, the same Wolfram I just explained, has the 3 video tracks. However, using these track selection options, which again have been renamed from what they were originally named in 12.1, to say I just care about the first track of this video. I don't want the narrations or the read through the bullfinch, the Eurasian bullfinch information. So if I specify this video object with just that selected audio track, all I get back in audio tracks is the single first audio track. All right, so another quick reminder that audio was a way for us to get a handle to the audio track of a video file. If a video like this video of a bullfinch has 3 audio tracks underneath, audio always extracts and links to the first track of that video. So in this case, this audio basically stores the natural sound of the bird on the tree. However, if I want to get handle to the second video track, second audio track, which ends up being the English description of the Eurasian bullfinch, I can do that with the audio track selection being the second track. And now here's the audio for that second track.
The Eurasian bullfinch is a small bird in the finch family.
And then that obviously, again, as I mentioned before, it can be passed through any audio processing function that we have in the system, such as speech recognize, in order to be processed, analyzed, and give us results, such as the result of the speech recognition here. Okay, so this was mostly about additions and updates to our video processing and analysis capabilities. On the side, we've added a lightweight video in a sense, which has been around for a very long time in some image formats such as PNG and GIFs, referred to as animated images. Our construct in the system is also called animated image. It can refer to a file, which can be PNG, GIF, and then HEIF or WebP also is coming in the next versions, or it can be constructed from a list of images. And as the illustration shows, we basically go from a sequence to this object, which is an animated image. So let's construct one from this example data that we have distributed in the system. I can get access to its information, again, such as duration, frame rate, and other image properties. There are a few number of image operations such as color conversion, resizing, padding, and cropping, which are added to support, which are updated to support animated image. So for instance, here I'm converting this animated image into a grayscale. Again, I think padding and resizing would be are a few other very commonly wanted operations. Not a whole lot more is typically done on these animated images. However, if somebody wants to do a custom operation, they can extract frames out, then map the operation on these frames, such as do a color replace of the blue background with a green background, and then put the result back into another animated image. Animated images can also be stopped and then played back in the system, like so. There has been improved functionality around face analysis. We have had fine faces and face aligned and facial features, in fact, which is missing from the list here before. We've added face recognize in version 12.2, which is basically creating a small face classifier based on a labeled set of faces. Here, for instance, I have just 3 faces and 3 labels, and I can run this call to perform a face recognition or the classification, and then ask for who is in this new picture. And then here is a multi-face recognition, similar face recognizer with that same data set, and I can ask for a bigger picture that all of the faces are detected and cropped. And now I'm asking for an image name or label from the data set that corresponds to that face and where that occurs. And then such a result can be fed to, for instance, highlight image to show the detection. This is a nice example, the Star Trek example that shows up in Stephen Wolfram's version 12.2 blog post, which really brings many things together. Here, the example shows a quick web search on Star Trek character. And for either of the characters, we get 10 sample faces, and this is not error-free. This has some outliers in it as well. If I run a face recognizer on this rather small data set, I get a classifier function. And then I can use this classifier function recognizer on the detected faces in the frames of this video, which if I switch to a minimal, this was basically a
reassigned for research purposes. I am going to.
This is a promotional ad. The link is in archive, can be looked at. The result of recognition over all the frames using this video map list construct or function can give us basically a complete set of recognitions over time. And then with a little bit of work, a list plot can be created to show characters and those we don't know based on our rather small data set. Who is showing up where in this, I believe, around half a minute trailer or the promotional video. All right, this is basically the last thing I wanted to talk about today. Useful both for image understanding and correction as well as video color correction. People are looking at image scopes a lot of times to balance for brightness or some colors and so forth. Histograms have been there for a long time in our system as well. The combination of histograms, vector scope plots, and waveform plots are very commonly used in video production to make sure the color balancing and brightness and place, where the bright stuff in the image is, has been really helpful and useful in practice. An image waveform plot, which can be used to show image intensity or Rgb waveform, is a plot that basically takes every column of an image, and it can be done over frames of a video, and plots color intensities over each column from left to right. And typically for cases, let me think, I is something different here. Okay, so there, where intensities are higher, so you see we have brighter spot or region in the center when we look at the columns of this image, and the waveform plot basically shows the brightness in this form, and that is shown for all our red, green, and blue channels. I can just look at the luminance channel, or I can plot the red, green, blue in a row, which is also known as an Rgb parade. That was an image waveform plot. Image vector scope plot is another plot that is also very commonly useful, has some reference colors and some ideal or target saturations. And basically showing the distribution of color in that space. Another variation of that is to use a color appearance, which instead of showing same color pixels, we show the color of those pixels as well to see where they all land. And this function, this plot function, has a lot of appearance elements that one can be used, what one can use to plot as a reference. And I'll just, for the sake of saving time, I'll just leave that to you guys to explore. That's it from me today. A lot of these information and examples can be found on our reference pages. Perfect start for all of these are going to be our root guide pages for image, audio, and video processing. I guess another important and useful place to look at is about importing and exporting video, specifically for FFmpeg installation. Thank you very much.